My name is Shankar Balasubramaniam. I'm from the Department of Electrical and Computer Engineering at The Ohio State University. Welcome to our first ever Ohio State ECE Unplugged podcast. In this series, we'll explore different facets of research in both ECE and OSU. So one of the lesser known facts about OSU that it's a very large, comprehensive university with an enormous research portfolio. The breadth of our faculty research expertise and their impact on society is enormous. To put some numbers behind this statement, our research expenditure last year was about $1.7 billion. I think it's in the top 10 of all universities in the country, maybe a little bit higher, but it's in that ballpark. And ECE's contribution to this part is about $27 million last year. We have a number of faculty who are at the bleeding edge of science and technology, and you're going to meet a number of them in this series. With that, it's my pleasure to welcome Professor Steve Ringel to our very first inaugural podcast. Steve has been here for 34 years. When I let Steve, and he's looking at me, he's wondering, 34 years and 8 months to be very precise. Well, I let Steve discuss his research. He is a highly distinguished and recognized scholar in his area. He's won numerous awards for his work over the years. He's a fellow of IEEE and AAAS. And in his spare time, he is the Senior Associate Vice President for Research at OSU. Mind you, in his spare time. So he's a perfect lead-in for this particular podcast as we explore his research and OSU's research vision. So with that, welcome, Steve. It's wonderful to have you here. I'd love for you to describe your research to a lay audience.
Sure. First off, thank you, Shanker, for inviting me, and it's an honor to be the first of the EC Unplugged podcast program. I think this is a fantastic idea, and it's humbling to be in this department for, I think it's 34 years and 10 months, actually. I was surrounded by so many great people, so many smart individuals, so many incredible students, and so much impact. And I've loved every minute of it, to be honest, or I wouldn't be here beyond 35 years, which I will be here beyond 35 years. So thank you very much for this honor. So what happens when you do research for 35 years is you do a lot of things. And so I'll try to take this at a high level and then break it down into some of the things that my research group in ECE does. Okay. So first off, I work in the area of semiconductor materials and devices. I suspect most people who listen to this will know what semiconductor materials and devices are, but just in case, semiconductors are really the foundational component of everything modern technology today, whether it's cell phones, computers, satellite communication systems, medical diagnostic devices. Nothing happens in the innovation world in these systems without innovating in semiconductors. And so a semiconductor, the word semi is very important, is really a material that somehow conducts electricity between a great conductor like a metal and a poor conductor like glass. And the unique piece about a semiconductor is that you can engineer and tailor the amount of electrical conduction that you can achieve. And this allows people to make amazing things like the transistor, which is one of probably the most innovative and transformative inventions of the modern several 100 years. And this has enabled so many things, but it goes beyond that, right? So when we think about semiconductors, we tend to think about silicon. You think about chips. You think about Intel. You think about these sorts of things. But in my work and in my group's research, we explore the boundaries way beyond that of silicon. We look at very unusual semiconductor materials that are used for things like solar cells, space electronics, very high-speed devices that allow us to do all sorts of broadband communication, that allow us to do this podcast, in fact. Many, many, many innovations have come out of this, and the industry worldwide that is semiconductors is broad, deep, and highly innovative. And so our research here is not, we're not producing technologies of the scale that, say, companies do. What we are looking at is the next generation. And in my group, we do this by doing a lot of what we call electronic material science. In electronic material science, what that means is we are looking at how to design and tailor properties, whether they're electrical properties for an unusual kind of a device that can be energy efficient, high voltage switching in, say, the future electric grid, or a very advanced high performance solar cell. Okay, I lost my train of thought. Two, looking at tailoring the optical properties of semiconductors as well as the electronic properties. So semiconductors is kind of like an old term, but the reality is these are just unusual materials that can be highly tailored and highly engineered for many properties. So my group breaks this down into really two focus areas. One is historically in my group working on advanced photovoltaics or solar cells. So photovoltaics is really the process of converting the energy of a sunlight, which is a photon, into an electrical energy form, which is an electron. Okay, and then transporting that current through a device, a load, to create power. And so the solar cell is an interesting story. Was originally invented at Bell Labs in the 1950s. It had nothing to do with replacing fossil fuel. It had only to do with the fact that very smart people at Bell Labs realized that if satellites could fly around the planet, you could have global coverage for telephone calls, which is clearly where we are today and way beyond that. It was a power source. It was a power source to live in space. I became fascinated with this because of two reasons. One is the use of semiconductors to create energy like this. And the second one is we have always had a big focus in my group on the impact of the space environment on everything that's a semiconductor in space, whether it is a solar cell, whether it is a device for, say, space-based radar, and what is the effect of the space harsh environments on the behavior of these materials and devices. How can we measure those effects? How can we mitigate those? How can we improve performance? And so a large part of our research is about that effect on semiconductors. And so the effect that we look at, and if you're in space, you probably have noticed that, astronauts wear spacesuits, and it's not just for breathing. Okay, you have shielding all around them and this and that. There's high energy radiation in space that is trapped in what's called the Van Allen belt, the gravitational forces around the planet. You have things called galactic cosmic rays, which sounds like an amazing thing to say that, but these are sort of like the remnants of basically the origins of the universe that are very high energy particles. These all create havoc. They blast into things. And so one of the things we care about is what happens to a semiconductor when it gets bombarded by these space effects. So what happens is you create, if you think about a semiconductor material for a moment, they're made of atoms, and they're in a crystal. And so if you have a very high energetic particle hitting such a thing, it can dislodge an atom. We call that an atomic defect. My group studies that. What is the kind of defect that's created? How can you avoid it from happening? How can you mitigate its effect on a device? And so much of our work is focused on that problem for space solar cells, but also for space electronics. So this is one very big area of our work, and we've had decades of work working with NASA, Space Force, Air Force, commercial companies, ESA, JAXA, all around the world looking at these problems. And it's a never-ending problem because there's not one that can ever be fully solved. And so it is a great area, but it's a great area of need, and so we focus heavily on that. So, okay, I'm not quite sure how I wound up in that total direction, but let me take a step back here and talk about solar. So I'm mentioning about space solar. What's interesting about solar cells, of course, I think most people realize that solar energy is of greater interest for dealing with, say, carbon-based fossil fuels, energy systems. And so, for example, I think people know that photovoltaics, if given the right amount of area, can basically replace most primary sources of energy that's used in the world today. So to give you an idea of scale, right now, as of I think 2 days ago, I was at a meeting in Washington, D.C., found that there 9% of U.S. base power, as 9, is now provided by solar. This is a very large number. It was less than 1%, less than 10 years ago. It was not measurable 20 years ago. Other countries are higher than that, but we all know the United States uses a lot of Earth-based energy. 9% of US-based energy is a big number. So solar has adapted from way back when Bell Labs was worried about using this to power satellites for space communications. Now is becoming really in my opinion, the most promising clean energy source in the world today that's not nuclear. Okay. And all of those innovations came from taking that original innovation and the original work and then looking at, well, how can we do this on Earth? And so in my own group, we did the same thing. The focus, the goal of a space solar cell, okay, is for performance. Okay, performance. Okay, because things have to fly, the limited area. On Earth, it's cost. It's how does energy, what's the cost of power produced by a photovoltaic array? How does that compare to, say, fossil fuel, coal, oil, gas? And so the metrics are very different. And so one of the things we started to do in my group was to ask the question, how do we take expensive, high-performance solar cells used in space and keep them high performance and make them much less costly on Earth? And so what we started to do was look into the primary issues of cost, and that is the manufacturability of those solar cells. And so right now, my group has worked heavily on using replacement, what we call substrates. These are materials that you deposit a solar cell on that are low cost, highly scalable, highly manufacturable, and very available. And how do we use that to basically address the cost question? Because on Earth, what we care and we all care about is what we pay on our electric bill, right? In the technology world for solar, we call that what's the cost per watt produced, okay, and at what scale. And so our group has actually done an amazing job because I've had very motivated, smart students and postdocs to have created a unique kind of solar cell which combines the high performance of a space solar cell with the low cost of silicon. Silicon is low cost because we have the silicon industry worldwide. So to give you an idea, a silicon wafer, 300 millimeter wafer, might cost $15. It's basically free. A 300 millimeter, that's 12 inches. Okay, a wafer, a substrate that's built of the kind of substrate that's used in space, which is using germanium, is half the diameter. So what is that? 1/4 the area? Is that right? I don't want to do math on a podcast. Half the diameter. Okay, costs about $2,500. So the listeners can do the math. Silicon is free. So silicon is manufacturable. Silicon is worldwide because of the integrated circuit industry. And so how do you leverage that is where we focus. So how do you integrate a space solar cell material with high performance with a very low cost, very available, very manufacturing ready substrate? So that's one of our primary two areas. So I'll pause so our host can jump in before we get to the second area.
Yeah, that is wonderful, Steve. So I wanted to ask you about impact and potential impact, but looks like you've addressed that in spades in some sense. So I'm going to ask you a slightly different question. As you look back in your time as a researcher, what impacts of the work that you've done, both in terms of radiation hardness that you talked about, as well as solar cells, are you immensely proud of? And what does the future look like? What piques your interest in some sense?
That's a very open-ended question for a researcher to answer. So let me think about how to prioritize that. Well, I'm interested in too many things. But I will tell you this, there are two areas that are mostly interesting to me now. So as we do this radiation work and as we study these foundational atomic defects, a couple of things we've learned. It is very hard to properly measure quantitatively the impact of those defects on a property that can be built into a device model for design. And so what we're working on right now is a very unusual set of experiments with a national lab where we are trying to parameterize the radiation displacement effect itself and what happens after you displace an atom where it moves around, it turns out, and it moves around in ways that are influenced by the operation of the device itself. So imagine if you're a high voltage transistor and you have a high electric field. you create an atom that is now in a non-equilibrium situation. It's bounced out of its happy little lattice site. And there's a big electric field because it's in a device. The electric field will influence the motion, right, of this atom that got bounced out. What does that mean? How is that measured? This migration of an atom, where does it go? Does it create a benign or a malignant effect on a device? Can we measure it? And if we can measure it, can we figure out a way to put properties of that into a model so that we can make better predictive design of how materials and devices operate in space? That does not exist. It exists, but not to the level necessary to do this properly. And so we're doing some really interesting, really physics experiments at this point in time with a lot of partners around the country to do this. So one thing I'm proud of is that we went from, I would say, materials and atoms into devices and systems. Now it's going back from device system down to materials. So we're kind of doing an iterative innovation process in a way. We're informing our basic science from what we know or don't know what might be happening at a macro level in space. So one thing is that entire arc is something I'm proud of because I wouldn't have predicted it. And we stuck with the scientific method. We follow the path, and what I'm proud of is the people have stuck with me in this idea. My group, my students, my former students, even my former students who are PhDs from our department, Shanker, are working on this project at several government labs with us now at their cost. It become that important of a problem. Okay, so there's that. The second thing that I'm very proud of, and by the way, that work we are doing not just on solar materials, but also on advanced semiconductors, a kind of technology we call wide bandgap semiconductors, which are used for things like space-based radar, things like this.
So this is just to this is
Sure.
for both.
Both.
Okay.
Both. The second thing is, and I cut myself off when I talked about our solar work going back from space to terrestrial, is our group currently holds the international standard record performance for the kind of solar cell that we build today here and other groups around the world build, which is a hybrid compound semiconductor silicon, what's called a tandem solar cell. So we're on now. We have a defined spot on the road. The IEEE has a technology roadmap for photovoltaics. We're on it. And we're, since 2020, the record holder in the world for this verified. So I'm proud of that. And I'm proud of the fact that this has now spawned a lot of efforts into other countries working on this with us, in Australia, India, Spain, Singapore. And I think that having this kind of excitement coming right from Ohio State is really key, because I've seen these maps in these papers, and what it says is you'll have, these companies or universities, and there it says Ohio State University, boom, right there on the charts. And I'm really proud of that, because I think Ohio State deserves the credit for supporting the work to begin with.
That's wonderful, Steve. So I'm going to ask you to put on a slightly different hat.
Sure.
So you are the senior associate vice president for research. So I want you to look at it from research at Ohio State, from that lens, and talk about some of the large initiatives that Ohio State is both interested in, if you can, from a high-level perspective, and where do you see opportunities for growth and impact?
Well, first off, let me explain what this job is, okay? And so in this new position that I have, it's really to translate what's worked at the department and at the institute level, because as you know, I'm the founding director of the Institute for Materials and Manufacturing Research, which is a very large organization. What translates from those experiences to the university level? So, to me, the key word is amplification. So if I look across the university, and you mentioned in your opening remarks, we're a very broad university with $1.7 billion of annual expenditure in research. So where's that research get expended, right? And how is it organized? And how do we catalyze innovative growth and not stagnate growth? And so my focus there is primarily on that, which is how to not just fortify existing strengths, but build on those strengths through efficient research that happen in centers and institutes, which are, of course, comprised of faculty and department psychologists. They're not disjoint entities. They're overlapping entities with perhaps more flexibility than an academic department when it comes to research. How do we build and amplify? How do we look at the national priorities? How do we look at the global imperatives? How do we look at the university priorities and imperatives? How much do we align, or how much do we influence what should be happening? Those are two equal things in the sense like alignment of existing strategies is fine, but I'd put the smart money on those who want to influence the next set of things all the time. And so my job there is very much to help the centers and institutes get the most out of who and what they are, help them achieve their goals, help them leverage as much of the university as they can, and likewise, how does this help our departments and colleges do appropriate, say, investing, faculty hiring, student recruitment, in these areas? And I think you know this very well. This is one of the reasons why I spent an awful lot of time trying to build these partnerships in other countries, in particular in India, in particular with IIT Bombay. This research center that we have, which has created now a dual PhD degree program. All of these are things that can amplify and multiply impact. And in so doing, our goal would be to have Ohio State be, even more obviously responsible for more impactful innovations in the world. It's helping people, helping lives, helping technology, helping national security, helping how do people age. These are some of the areas that the university is looking at right now. But really, it's more than just writing papers. It's more than just funding. It's really like, how does Ohio State become the most impactful thing it can be in the areas that matter in the next 0 to 50 years? And so I believe that a lot of those things happen through center and institute contracts for one very easy reason. It's the natural place where teams form. So we always talk about we have to be interdisciplinary. Well, how do you do that? Do you just throw out a seed grant and go, please work together? That's fine. Maybe it gels, maybe it doesn't. Or do you have an asset that more than one group needs? So you have a capability that says, oh, I have a group in medicine that wants to work on this, and I have a group in electrical engineering that wants to work on that. And it turns out they need the same thing at the same time. And so they collide, they collaborate. And so I'm a big believer in creating that third place, where the third place is kind of a neutral place where parties can come together. And to me, a university is sort of the most ideal scenario for that to happen. And so very much I'm focused on that in my role as a senior AVP here at Ohio State.
So with that, Steve, thank you so much for talking to us. Just my closing remarks, Steve has been a wonderful citizen of the department and the university. And he's been at it for 34 years. He's one of the most selfless people I know in terms of donating his time. So with that, thank you very much.
Thank you. It's been a real pleasure to be here and be on this podcast. And I'm really excited to hear what my faculty colleagues are going to talk about and learn about what they're working on through this mechanism. So thank you.
Thank you.